Hi, the PIO chip is a good friend of the Z80 CPU. It's a two-port programmable parallel input-output device that provides a TTL-compatible interface between peripheral devices and the Z80 CPU. The pin assignment looks like this. The first channel, called channel A, has 8 different input-output ports and 2 hardware handshaking pins called ready and strobe. This is identical to the channel B. There's also an 8-bit data bus for communication with the CPU. The device can generate hardware interrupts with pin 23. If enabled, the Z80 should run in interrupt mode 2 to handle the different vector addresses. The PIO belongs to the Z80 chip family, which means the devices can be daisy-chained with interrupt enable in and interrupt enable out. If you're not familiarized with the Z80 interrupts, you should watch Interrupts Part 2 with the Zilog Z80. You can find a link in the description. The PIO is not addressed over classic memory address, but over the port-mapped I/O. If you don't know what that is, you should watch the video, Part 8 of Programming the Intel 8080, 8085 and Zilog Z80 in assembler. Link is in the description. The microprocessor 1 is the device which I will use in this video. In the MFP1 you can address a PIO chip at 4 port-mapped addresses, from the hexadecimal values 80 to 83. DA stands for data channel A, DB for data channel B, and CA stands for control channel A, control channel B. With the control ports you program the behavior of the respective channels. How does the chip know it is addressed? A port-mapped access is done over the I/O or Q pin, which is negated. 0 means it's selected. If A7 is 1 and A6 is 0, the hexadecimal value is 80. One of the outputs of the 74LS139 decoder is directly connected with the chip enable pin of the PIO. With pin 6 you choose between port A or port B, and with pin 5 you choose between data or control mode. For that, let's have a look at the circuit diagram. Here is the PIO chip. The selection between port A and B is made over the address line A0, and the selection over data or control mode is realized over the address line A1. So if you want to address data on port A, A1 and A0 are 0, which results in 80. To access data B, A0 is 1, which will result in 81. To access control port A, A1 is 1, which results in 82. And finally, for control port B, where A1 and A0 is 1, the address is 83. I want to mention that the interrupt enable in pin from the PIO is directly connected to the interrupt enable out pin of the CTC chip, which means that the CTC has a higher priority than the PIO. When the CTC is in an interrupt, interrupts for the PIO are disabled. Channel A has 4 modes. Mode 0 for output, Mode 1 for input, Mode 2 for bidirectional, and the third mode is bit control. Channel B has 3 modes: output, input, and bit control, and the bidirectional mode is missing. If you put channel A in bidirectional mode, channel B has to be placed in control mode. We will see that in part 2. Choosing the mode is done over the selecting operating mode byte. The 4 lowest bits must be 1. We don't care about the value in D4 and D5. And with the 2 bits D7 and D6, we select the desired mode. 2 bits can handle 4 values from 0 to 3. So if you choose output mode 0, the value is 0, 0, so output mode is 0F. If you choose input mode, the value is 1, so 0, 1, and the hex value is 4F. If you choose 2 bidirectional mode, the binary value is 1, 0, so the hex value is 8F. And if you choose the last mode, which is bit control mode, the binary value is 1, 1, so 8 and 4 is 12, and 12 in hexadecimal is C. The value is CF. If you want to configure port A in output mode, you have to load the accumulator with the hex value 0F and send the value of the accumulator over the out instruction to the address 82. After that, the port A is configured for output. With the instruction out to 80, you send the value of the accumulator to port A. After the value has been written, the ready signal goes from low to high, indicating that data is available for the connected device. Then the peripheral sets the strobe signal to low when it's reading the value from the PIO. And with the rising edge of the strobe signal, an interrupt is generated when enabled on the PIO. Finally, the PIO sets the ready signal to low. Let me switch to the datasheet of the PIO to show the exact timing. This is a clock signal, so after the value has been written to the port, so with the rising edge of the white and the next falling edge of the clock, the ready signal is put to high. And when the device which is connected starts reading the value, the strobe signal is put to low. And when the device has finished, it will raise the strobe signal, and immediately, if enabled, an interrupt is generated by the PIO. And with the next falling clock signal, the ready signal is put to low. In the Z80 interrupt mode 2, you specify the interrupt vector with 1 byte. The lowest bit must always be 0, so that the address always starts with an even number. To load the port interrupt vector, you do it with a number where the lowest bit is 0. For example, if you send 0 to 82, this will set interrupt vector 0 to port A. If you send 2 to 82, this will set interrupt vector 2 to port A. Finally, you have to enable the interrupt for the specific port. The instruction to do that is done with the following command. The lowest 4 bits are 1100, and with the most significant bit, you enable or disable the interrupt. With 03, you disable the interrupt, and with 83 you enable it. If you want to put port B in input mode, you have to send 4F to the address 83. Now the port B is in input mode. When the connected device wants to send data, it will put the strobe signal to low only when the ready signal is high. With the lower strobe, the PIO loads the value immediately, and with the rising edge of the strobe, an interrupt, if enabled, is sent, and the ready signal goes to low. As long as the ready signal is low, the connected device won't send any further data. Now the CPU has to fetch the data from the PIO with the in instruction. After the ready line will be put to high again. Let me switch to the datasheet again to show the timing. So this is the clock signal again, and when the device wants to send data, ready line is high, so is the strobe low. It will tell the PIO, oh, data is available. The PIO reads the data immediately, and with the rising edge of the strobe, if enabled, an interrupt is sent, and with the falling edge of the clock, the ready line goes to low, and it will stay low until the CPU has read the value. With the rising edge of the read and the next falling edge of the clock, the ready line will be put up again. I think it's time to look at the source code. Here I've defined a few names. Scan is an internal system ROM function which will wait until a key is pressed. And this is hex 7, also an internal ROM function which will convert a hexadecimal number into its 7-segment display format. This is the 8-bit upper address of the vector address table. And this is interrupt vector address for channel A, interrupt vector address for channel B. This is enable interrupt of the PIO, disable interrupt of the PIO. This is the data for channel A, data for channel B. This is a control channel for A and control channel for B. And here is the mode 0, which means output mode, and mode 1, which is input mode. Loading the special I register with the 8-bit upper vector address, setting CPU in interrupt mode 2, enabling interrupt. Here is setting channel A in output mode 0, sets interrupt vector for channel A, and enable interrupt on channel A. And the same for channel B, but in input mode, setting interrupt vector and enabling interrupts. Loading IX with the LCD, that's could say a video memory address. This one will read the keyboard input and writes the LCD buffer to the display. Here I will send the value of the key to the data channel A, converting it to the 7-segment format, and writing it on the left. That's the first digit. So I will write the input to the first digit, clearing the accumulator and erasing the last digit, and jumping back, so it's an endless loop. Here's LCD memory address, and at address 1A00 I will define our interrupt subroutines. So this one is interrupt routine for output, saving the accumulator and the flag register, and loading the accumulator with an O, so an lowercase o, and writing it on the right digit, restoring the accumulator and the flag register, enabling interrupts and return from interrupt. And here the same for interrupt routine input, saving the accumulator, reading the value from data channel B, converting it to the 7-segment display, and writing it on the most right digit, and restoring accumulator, enable interrupt, and return from interrupt. Yeah, that's basically all. Let's enter the code in the MPF-I. This is a microprocessor board 1 with a Z80 CPU and the Z80 PIO chip, which has the same size as the CPU. I've connected an Arduino to it. From the PIO, the channel A, I've connected PA0 to PA3. That are 4 pins, and also, of course, the ground and the ready and the strobe signal. And for the channel B, I have connected only 2 signals from PB0 to PB1, and the ready and the strobe signal from channel B. Okay, it's time to enter the code at address 1800. Years later, I have to enter the vector addresses for the subroutines. 0, 1B and 0, 1C. Quick check. Okay. Terminal is connected, so let's start the program. I type 0, works, 1, 2, 3, 4, 5, 6, 7, 8. So the O here is from the subroutine, from the interrupt routine. 9, 10, 11, 12, 13, 14, 15. So if I type a 0 on the terminal, the interrupt routine writes 0 here. If I type 1, it's 1. If I type 2, it's 2, 3, and that's a maximum, because I have used only 2 bits. Let's go back to the studio. A big thanks to the lab. So, what's left is the bidirectional and bit control mode. But I will cover that in the next part. Thank you for watching. See you. Bye bye.